You hear so much about the potential of quantum computing, right? Solving these massive problems.
Absolutely. The power could be revolutionary.
But that power is incredibly delicate.
Right.
The biggest hurdle really is noise, errors creeping in constantly.
That's the central challenge. And today, we're diving into a key piece of the mathematical toolkit designed to fight back against that noise.
We're talking about the Clifford group, often written as C sub n.
Exactly. If you're serious about building quantum systems that actually work, especially with quantum error correction, QEC, you really need to understand this group.
So our mission today is to unpack what it is, look at its fundamental building blocks, the gates, and uncover this, well, frankly, surprising property it has.
A property that shows us this interesting boundary between what's truly quantum hard and what, perhaps unexpectedly, a classical computer can still handle efficiently.
Okay, so let's start at the beginning. The sources say the Clifford group is defined in relation to another group, the Pauli group.
That's right. The Pauli group, P sub n, is sort of the foundation here. It's built from the Pauli matrices, identity, X, Y, and Z, applied across in qubits.
And these represent the basic errors, like bit flips.
Precisely. The Pauli group essentially describes the common fundamental errors. Bit flips, which is the X matrix, and phase flips, the Z matrix. Y is just a combination, and identity means no error. It's the set of things can go wrong at the most basic level on your qubits, possibly with a phase factor like plus or minus 1 or plus or minus I.
Got it. So if the Pauli group is the set of errors, what does the Clifford group do with respect to these errors?
Okay, so the Clifford group, C sub n, is defined as the set of unitary operations, let's call 1V, that normalize the Pauli group.
Normalize. What does that mean practically?
It means if you take an operation V from the Clifford group and you apply it to an error P from the Pauli group, like VP dagger, the result is still an element within the Pauli group.
Ah, I see. So a Clifford operation might change one type of Pauli error into another type, maybe an X into a Z or some combination, but it never turns it into something weird, something outside that defined set of Pauli errors.
Exactly. It preserves the structure of the Pauli errors.
Mm-hmm.
It maps the set of Pauli operators back onto itself. This tidy behavior is crucial for error correction.
Okay, that makes sense. And what specific quantum gates allow us to perform these Clifford operations? Is it a huge list?
Surprisingly, no. That's one of the elegant things. Any unitary operation in the Clifford group can be constructed, up to an overall phase factor, which doesn't matter physically, using just 3 fundamental gates.
Only 3.
Just 3. The Hadamard gate, often it's just called H, the phase gate, S, and the 2-qubit CNOT gate, controlled NOT.
H, S, and CNOT. So these are the Clifford gates people talk about.
Those are the generators, yeah. Build any circuit using only those, and you're performing a Clifford operation. They're absolutely fundamental for building fault-tolerant quantum computers.
Which brings us directly to why these gates are so important. Quantum error correction. How does preserving that Pauli error structure actually help fix errors?
Well, QEC codes work by encoding a single logical qubit across many physical qubits. Then you need to check for errors on these physical qubits without, accidentally measuring and destroying the fragile quantum information you're trying to protect.
Right, you want to diagnose without disturbing the patient, so to speak.
Exactly. Clifford gates are perfect for this. You can use circuits built from H, S, and CNOT to measure something called the error syndrome. This tells you if an error occurred and generally what kind of error was, like an X error on qubit 3 or a Z error on qubit 5, all without revealing the actual logical state.
Because the Clifford gates just shuffle the Pauli errors around, they let you detect that error signature.
Precisely. They allow you to query the system in a way that only reveals information about the errors which belong to the Pauli group, enabling you to then apply a correction.
It sounds incredibly elegant, a perfectly contained system for managing errors. But then there's the twist, the Gottesman-Knill theorem.
Ah, yes. This is a really profound result. It's kind of the aha moment about the Clifford group's true computational power.
What does it say?
The theorem states that any quantum circuit composed only of Clifford gates, so circuits using just H, S, and CNOT gates, plus preparing qubits in standard initial states like 0 to O-Tanner, and performing measurements in the standard basis, can be simulated efficiently on a classical computer.
Wait, hold on. Efficiently simulated classically, so the very gates that are essential for protecting quantum information don't actually provide a quantum speedup themselves.
That's the paradox. They're absolutely necessary for building stable, error-corrected quantum computers. You need them for fault tolerance, but the computations you can perform using only them. A regular laptop could, in principle, keep up.
So they provide stability, but not the exponential advantage we expect from quantum computation.
Exactly right. Their nice, clean mathematical structure, the very thing that makes them great for error correction by keeping Pauli errors neatly contained, also makes them, well, classically tractable.
So to get that true quantum advantage, you must include something else.
You absolutely must. You need to introduce at least one gate that is not in the Clifford group. Gates like the T-gate, for example. These non-Clifford gates are sometimes called magic states or resource states when used in certain schemes. They break that clean structure and push the computation into a realm that classical computers struggle with.
Wow, so the Clifford group forms the essential, stable foundation, but the magic happens just outside of it. Understanding these boundaries is so critical.
It really is. And understanding boundaries, capabilities, and where the real leverage lies, that's crucial not just in fundamental physics, but also in applying complex technologies like AI today.
That's a great point. Making those connections is key.
And speaking of applying advanced tech, this deep dive is brought to you by Embersilk. If your business needs help navigating the complexities of AI, things like training models, setting up automation, integrating systems, or even just figuring out where AI agents could provide the biggest boost, you should check them out.
They help uncover that impact, whether it's for business or even personal projects. Find them at embersilk.com for your AI needs.
A very useful resource.
Okay, so let's recap. The Clifford group is this essential set of quantum operations defined by how they interact with Pauli errors.
Generated by just H, S, and CNOT.
And they form the backbone of quantum error correction, allowing us to diagnose errors without destroying quantum states.
Providing that crucial stability.
But surprisingly, computations using only these gates remain efficiently simulatable classically.
According to Gottesman, Knill, yes.
So the final thought to leave you with is this. While the elegant structure of the Clifford group is fundamental for building reliable quantum computers, the true exponential power that promises to change the world seems to lie in carefully stepping outside that structure.
That's where the quantum magic really seems to begin. It's the edge we're all exploring.
Fascinating stuff. If you enjoyed this deep dive, please do subscribe to the show.
It helps people find us.
And hey, maybe leave us a 5-star review if you feel like it. It genuinely helps get the word out. Thanks so much for tuning in.